So hello everyone, I'm Murali Emani, and I'll be talking on some of the works that we are doing on as part of the ALCF AI Testbed and how we can program these new AI accelerators that we have currently deployed. So as we have seen, it is the evolution of the systems at ALCF, looking at the timeline. So we have come a long way. And more recently, as you're aware of, so we have the Polaris supercomputer with NVIDIA-based A100 GPUs, and our latest addition is the Aurora supercomputer with Intel GPUs. So these are our production-ready and leadership supercomputers that we are deployed for running science applications. And we've also seen an emergence in the applications which use a lot of AI and ML in their codes. So we started a small testbed a couple of years back, primarily to deploy these new AI systems to understand how they run for, how they perform for different applications, and see if we can use them in addition to these supercomputers to accelerate science. So a quick primer to that. So for example, so why do we need a different type of hardware architecture? So here is one example use case. So on the top, we see there's a simple model here, which a bunch of different layers. On the left-hand side, we see like how this application or the model is mapped onto a traditional, say, GPU-based system. Now, for example, so each layer is kind of launched sequentially one by one, and there'll be some overhead when you are launching these kernels and some overheads on the memory bandwidth when we do them on a sequential basis. So here we see that so there's the convolution one layer, then there's a pooling, there's a convolution two. So and there's some context switching happening while the kernels are being dispatched and launched onto the device. On the right side, we see a kind of a different approach that's called a data flow way. So here is an example from a chip called Sambanova SN30. So how they do is, so the chip is composed of different compute and memory units. So here we see there are a bunch of PCUs and PMUs. And when we look at, you're taking this model and we are kind of putting them or mapping them onto this chip, so that can be done spatially. So if you see, the first layer is mapped onto few units, and the second layer is mapped onto few units. So the data is moved or transferred across this bunch of PCUs and PMUs, and that's why it helps eliminate the memory traffic and overhead. Now, why this is important? So we are seeing there's a tremendous increase in the model complexity, and even the, for example, the resolution of the images. So we are trying to fit them on our traditional, say, GPUs, for example. So they may be hard to fit on the compute that's available. So we may need to run them at large scale, and it might take a while for running these models. So there has to be a different approach to kind of optimizing them. And that's where the AI accelerators come into play. So it's a mixture of both the innovations in the hardware along with the software that can help mitigate some of these issues. So we call an AI accelerator. This is a high performance parallel compute machine, which is kind of specifically designed for working on the AI workloads. For example, we have seen even the GPU is kind of an AI accelerator, and there can be massive multi-core scalar processors or the data flow architectures as well. Now, some of the key advantages that we see with these AI accelerators is there can be potential improvement in for the AI model performance, especially if you're doing some training and inference-based jobs. And as I mentioned, with the unique hardware and the software features, so we are able to deal with large complex models and also handle high resolution data sets. Even they are typically possible on traditional systems, but again, when we talk about expanding them on this in terms of the model complexity, so we are able to leverage these changes or the new hardware and the software systems. And again, some of the runs, they could also lead to more power efficient implementations. So this is a quick snapshot of the AI chip landscape. Again, this is quite old, maybe a couple of years old. If you see, there's a lot of interest and a lot of work happening across the spectrum, or like all the tech giants or systems in the startups. They're coming up with their own custom chips, which are kind of tuned to run these AI applications. And given there's a lot of emphasis on the emerging workloads in the AI space, so it's kind of interesting to understand which systems perform better and how we want to understand them as we kind of incorporate into our offerings at the LCF. So we started with this AI testbed where we have some the initial deployment. So right now we have these 4 systems that are available in for production use. So we have the Sambanova SN30. So this is an 8-node configuration, and each node has 8 reconfigurable data flow units. So you can think of an RDU as an equivalent of a GPU, for example. So we have like 64 RDUs for Sambanova. And the Graphcore system, we have 4 nodes with 16 IPUs, so they're intelligent processing units. And for the Cerebras CS2, it's a wafer scale engine, and we have 2 of those. And the Groq system is primarily an inference-based engine, and we have 9 nodes and 8. They call it as a tensor streaming processors. So at a very abstract level, you can think of this RDU, IPU, TSP as something which is the core compute unit, and as say an equivalent to an A100 GPU. So a quick high-level snapshot of each of these. So the Sambanova SN30, as I mentioned, so we call the chip as an RDU, and the RDU is broken up into multiple tiles. So we have 8 tiles, and there are a bunch of memory and compute units per tile. And the jobs can be run on a bunch of these tiles, and we have access to terabytes of off-chip memory as well. And the Cerebras system is they call it as a wafer scale engine. It's a pretty massive compute chip. If you look at this picture, so kind of showing the size and the dimension comparison of the wafer scale engine versus the NVIDIA GPU, and kind of characteristic by the massive compute that this the wafer scale engine offers. So you see this is kind of traditional, say, GPUs versus these AI accelerators, so how they are different. And the Cerebras, so again, the working board is called as a wafer scale cluster, where it houses a bunch of different dedicated nodes called MemoryX and Swarm nodes. And so basically these nodes help in kind of running much larger models on the Cerebras CS2 clusters. And now coming to the Graphcore IPU. So if you look at this picture, we are showing a kind of very pictorial representation of how the IPUs differ from, say, CPU and GPU. The CPU is primarily designed for scalar processing, whereas GPU is primarily for SIMD architectures, and there's large blocks of compute kernels and dense contiguous data. Whereas IPU is kind of unique in that sense, it has this massively parallel MIMD architectures, and it kind of helps in running the high performant ML applications. So if you see, this is a pretty, it has a very diverse characteristics compared to what we know of CPU and the GPU. And again, I'm going through very high level overviews of each of these systems to help understand how these differ from a traditional systems. Again, this is a Groq chip. So as I mentioned, Groq is primarily an inference-based engine. You see there are a bunch of dedicated hardware units to run or to accelerate the core components of any workload. If you look at the scale, the Groq chip is the single chip here, but again, we can scale out to a Groq rack. So right now we have a single Groq rack deployed at LCF. So here is a table which shows the hardware and the software support for each of the systems. So we have also included Habana, Gaudi one, but the 4 machines, the first 4 are available for the production use. So quick takeaway from this table is each of the system is totally different from one another. So either it has pretty massive amount of compute cores or pretty high or large memory capacity per accelerator, and they're kind of different from what we are used to running on the, for example, the NVIDIA-based systems. And again, each of the system has their own software stack to run a model onto their system. So usually they're built, say, on top of our standard programming frameworks like PyTorch, but the software stack is customized to map the application or run the code efficiently on that particular platform. So if you're taking a model, so we might need to make some changes to the code to enable to run on each of these systems. So at the AI testbed, so we have done some work on taking some of the science applications, which are usually run on our supercomputers, and we try to evaluate how these systems are very capable of running these applications. For example, we have ported, there's a cancer drug response prediction application, there's a Bragspeak from the imaging sciences, and there's protein folding. And more recently, there's also one application that's a Monte Carlo particle transport simulation code. There's a blend of the core AI applications, and also there's an emerging trend of running the plain or the traditional HPC codes on these systems. And we have seen a pretty good performance benefits of porting these models. Again, there are also some challenges like getting or porting these applications onto these systems, getting them functional, and getting the best performance is possible, and it requires some effort. So I give a quick example of how these systems compare for a workload. So here we're taking a model or science application called Genesalem. It's a genome scale language model, and this is built on a foundation model as a GPT-NeoX based code. So here we are running, for example, this table here shows the deployment on the A100 from NVIDIA. There's SN30, Sambanova, and Cerebras CS2. And if you look at the throughput so we are able to see that at least the SN30 and CS2, we are seeing a pretty high improvement in the throughput when we compare against the A100 as a baseline. And even the last column here also shows the energy efficiency, which also shows, so these systems are able to yield energy efficient runs as well. Again, this is one quick example. There are a bunch of different use cases that we have shown, and we also worked on some of the standard applications or benchmarks onto these systems. Like there's we have worked on like 2 papers which showed how the efficiencies of traditional deep learning primitives, UNet, BERT models, and even the LLM space, like a transformer benchmark and the GPT model. So we have done some rigorous evaluation across these systems. And again, so we conduct a lot of detailed training sessions on all these systems, along with tutorials at venues like supercomputing at SC. Again, then the next series of the AI testbed training is starting next month. So please sign up if you're interested. This will be more deep dive on each of the system, and it will be like a 2-day sessions for each system, and will be 4 hours roughly. It's a virtual session. So we'll be covering topics into more detail on the hardware, the software, how do you take care of your model and try to run on these systems, understand the performance. So I would strongly encourage to sign up for this upcoming testbed training series. So again, there are some useful links here. There's a lot of documentation available on the AI testbed page, as well as slides, and even the video recordings of our previous training sessions are also available if you're interested. Yeah, and again, there's a lot of folks who are working on this hands-on. So what we have done is for the hands-on session for each of the system. So we have put some test scripts that you can just try. Now, maybe let's start with Sambanova. As we have seen, as I mentioned, so the deployment that we have is we have 8 nodes, and there are 8 RDUs per node. So total 64 RDUs. So they are they're denoted as SN30 R1H1 R1H2 all the way till R4H2. So the way we connect is we first SSH to our login node, which is sambanova.alc.nl.gov. And so the password here is our mobile pass plus code that we use for other systems. So again, so we are kind of used to running on Polaris, which is the Colab or Jupyter Notebook for the AI system. So we kind of log onto the machine and submit scripts. They are like the schedulers which will help in running those scripts. So once you log on to the login node, you can actually SSH to one of these nodes. So it's a simple thing like you do SSH to say, for example, SN30 R1H1. But again, there are also the total of 8 nodes that you can log into. And so we've kind of listed some prerequisites. So for each of the system, and that can help to setting up your examples and maybe building any virtual environments if required. Yeah, so I'm currently on the SN30 R1H1. So what I did was, so we have provided some sample examples and the instructions to do so, which I've already put them here. So for this hands-on, we'll be using a BERT example, but again, there are other applications, other examples that you can definitely try it out. So how do we do is, so we have the scripts already provided. So here we are looking at a BERT large example. So we can just run the script called bertlarge.sh. So it will have steps for both compiling and running the model. So in Sambanova, when you compile the code, it will generate a file, something called as a PEF file.pvf. So this PEF file will contain information on how many units or how many PCUs and PMUs that a model requires. And once we have the PEF file, we can use that for running our example. And there are instructions on doing that. And if you look at the script that we have, we're setting up the environment, for example, and so here we are doing the first step as a compiled step here. So we're passing this option here and all other, like the model name and other parameters to the model. And once we have the compilation finished, so then we'll launch the run script. Again, as I mentioned, we'll be using the Slurm scheduler, so it will directly use or launch the job using SBatch. And there are some options that we use here. For example, in this case, we are using these 8 RDUs. So each instance of this BERT will run on half a RDU, or as I mentioned, there are 8 tiles per RDU, so it will be using 4 tiles, and we'll be learning multiple copies of those. And again, we can change this based on our requirement, and we kind of run our run script. So one thing is to be noted that sometimes the compilation can take a while. And I would say like just submit the script and it will be in the queue. And once the compilation is, it will also launch the particular job. So let me. If you see, so the output is kind of generated and it's dumped onto this bertlarge.out. So if you want to check the status, so maybe you can open a second terminal, log into that Sambanova machine, and you can check the output. And since we're using Slurm scheduler, you can also see the status of your jobs using the command SQ. So it will tell you what jobs are pending, what jobs are in the queue. So yeah, so a quick look at the current output file. So we see the code is being compiled. It generates a bunch of output logs. Again, as I mentioned, so this can take around 10 to 15 minutes roughly. And once the compilation is done, we can check this file for the output of the run. And so we have also included some other instructions. So for example, if we want to, as a homework, for example, if you want to understand what these flags are, Like for example, the number of tasks. You can change that, and basically it changes the way how many copies that we are running and see how that can affect its performance. Again, it requires a simple tweak to the your script, and then you relaunch it. So one thing is that the PEP file will have to be regenerated again, and again, the same compilation time will be included. And in this page, we also include additional resources. For example, so this is the first link, again shows the Sambanova documentation at our page, and this is again a detailed documentation available on the Sambanova page. Some other applications are also included. There's the scripts to launch them. You can feel free to take a look and just try some of the examples that we have. All right. So again, this is kind of the 101 getting started on the systems and trying to run some sample examples. So one thing again for Sambanova is that each of these examples, they have this, the virtual environment is already pre-built, so they're kind of directly launching them. So maybe next, let's switch to, so we see this code is running. So once it's compiled and just runs, so we'll see the output even in the SQ command. So next, maybe let's switch to the next system, the Graphcore. So here is a snapshot of the layout of the Graphcore system at AI Testbed. Again, it's the same way that we kind of access it. So from our local machine, we SSH to one of those login nodes. We have 2 login nodes. And once you're in login node, we can SSH to one of the 3 the compute nodes. Again, we have like total 4, but the first one is mostly for the management nodes, so we don't have SSH to that. Again, once we launch a script, we can actually access the IPUs from all the 4 nodes. So if you look at this, so there are 64 IPUs that you launch from one of the scripts. So once you log onto that machine, as I mentioned, you can SSH to one of these compute nodes, O2, O3, O4. So again, for the Graphcore system to run these examples, so you need to set up a virtual environment. So we have listed the steps here. And again, it might take a while to get this virtual environment set up. So we can just start with that for now. And so once the software environment is set up, we have a couple of examples that we can get started. So Graphcore actually provides this repository of these examples, and you can just clone them and try running some of those. So for this hands-on, again, we'll be using the same BERT example. The details are also listed here. In terms of the job submission, again, we use the Slump scheduler, so you can use srun or sbatch. Again, getting the status through SQ or cancel a job within is cancel. For example, here again, we are showing this a BERT model running on the IPUs. So here I've logged on to one of the login nodes. As I mentioned, so there are 2 login nodes, and say let me hop onto one of those compute nodes here. So once we are on this compute nodes, I've already set up the virtual environment, so I can just activate that. So now we have activated this the PopTorch environment, and so we can use we can just run this example using the srun command. So let's switch to the PyTorch version of it. setting up the environment and building requirements specific to this particular application. In each of these files, again, we have kind of provided a snapshot of what's the expected sample output. For example, if you're running this particular BERT example on 4 IPUs, so you should be able to see the output like this. So we are seeing how's the device allocation happening. All the layers are mapped to different IPUs, and at the end you see some training metrics. And besides BERT, so we've also included some other examples here. For example, there's a small, simple the MNIST code. It should run pretty fast. So it's just running on a single IPU, and again you should see an sample output like this. And one way we can also do is kind of, when you're trying this example, we change some of the parameters such as the batch size or the number of epochs, and then see what's the impact on the accuracy. Okay, while that's happening, so maybe let's try this simple MNIST example. So let me log on SSH to the other compute node. So now I'm on the second compute node. I'm trying a simple MNIST example. Tutorials, applications, MNIST. So again, we do the same steps. We kind of activate the virtual environment, and we kind of launch this job using the S command. Let's see that the Slurm scheduler will queue up this job. Then once the resources are available, so it kind of launches this example. Yeah. So while it's happening, so I'll also point you to some of the, for example, for the homework, you can just take this BERT or MNIST example and maybe try changing some of the hyperparameters of the model and report what's the performance changes that you see. Yeah. So here you see the job is now, script is launched. The job is running on a single IPU here. And we see first there's a compilation phase, and then you see model running. You can get examples if you want to launch, say, for example, a GPT-2 variant that's all listed here. For people who are kind of interested on understanding more detailed performance aspects, so there's a tool called as a Pop Vision Graph Analyzer. So it's kind of a performance profiler that's also available on this Graphcore system. And there are instructions listed here on how do we run or invoke your code, and you want to generate the logs for understanding how the model runs on these IPUs using this particular tool. Okay. There's an error. Fabric IPU. Maybe I can just relaunch that. So here, for the BERT example, so we have everything set up. We can maybe even launch that. So again, it's the same. So the job is queued up by the Slurm, and once the resources are available, so be running on the IPUs. And if you look at the code as well, so we can use some of these parameters like how many IPUs that we want. So here we are mentioning we want like 4 IPUs to run this particular example, and we are using this config file, and that can be tweaked, and like some of the input files that are present here. So we're using a wiki corpus sample for this particular example. All right, so yeah, the slab will be scheduled, and it'll start running once the resources are available. All right, in the interest of time, so let's keep, so it's been, okay, the job is running now. Maybe next, let's switch to the Cerebras system. As I mentioned, Cerebras is a big wafer scale engine, and we have two of those that are at the AI testbed. Again, if you look at the snapshot, so we use the same way. So we, from a local machine, we SSH to so one of those login nodes using ALCF credentials, and again, there's a prerequisite to before launching or running these examples to create this virtual environment. So we have provided these instructions here. How do you set up that? So once we have this virtual environment, so what we do is, so we have a bunch of models which are available using this model zoo repository. Maybe you can also show that. Yeah, so Cerebras models, again, it has a bunch of examples that you can just try them out. So for now, let's start with a simple model as such. So for Cerebras cluster, it has its own internal scheduler. It's a Kubernetes-based system that helps for submitting your jobs and queuing up. And once you launch these jobs using the Python script, so these are all automatically started. And similar to using an SQ with Slurm scheduler to get the status of the jobs. So on the Cerebras system, so we use a command called csctl. So that will, for example, csctl get jobs will show what are the current jobs that are either running or are pending to be scheduled. Yeah. So here we see for the Graphcore, the bird code is running. All right. So for the Cerebras system, so I'm on one of those login nodes. So once you SSH to one of using the cerebras.ai.alc.gov, so you'll automatically be put on one of these 3 nodes. And I've already shown this model zoo repository, and I'm in this particular BERT example directory. So again, so once we have here, so we want to activate our virtual environment. I'm already in that. And so there are this specific configuration files that we want to use. So we can use this command to copy them to this particular file. Now, how do we run this particular job? So we provided the command for doing that. So basically, if you look, so there's a run.py is the main entry point to run any job. And we are using the CSX to mention, like we are using one CS here. You can label each job based on, for example, the model here we're using the name as bird PT. And we have used these configurations so that we have copied in the earlier step, and we are passing those parameters. And there are other options as listed here. And even with the particular system, so again, there's again the phase of compilation and run. So we'll just run this, and now once the job gets scheduled and run, so you see it's kind of initializing, and we can quickly check it, what the current status is. So there are no other pending jobs at this time, so it should run right away. Yeah, see that it's kind of started its execution. And once the model is run, so you should be seeing an output, something like this. So we kind of put this an example snapshot, so that will help you understand how the output works when you are trying to run these examples. And yeah, if you see for in this the log that we provided, it kind of runs for say 1,000 steps, and we see how the loss goes down, and we also see the throughput rate and samples per second. And once the training is completed, so you get this output towards the end of the log. Yeah. So if you see this with status with CACTL get job, so you see this, I'm running this particular job, it's kind of running. So once the job is done, you should be able to see the output as listed. Now, apart from this BERT example, so there are also, like, yeah, for example, for the homework case, you can try with different batch sizes and see what's the performance difference that you observe. And again, there are other examples that we have listed. For example, there's a GPT-J implementation and also a GPT-2 variant. The other resources that we have linked are some of our internal documentation, and there is a documents Cerebras page, and again, there's Model Zoo repository as well. So there are a couple of steps involved here. As I mentioned, the compilation could take a while based on the model size. And all the scripts that we have provided include the steps to run and compile and run the codes on these systems. So it would be just a single script to launch, and that would take care of things simply. So again, now, for example, if you want to cancel one of these jobs, so you can get the name of the job from the first field with CACTL get jobs. You can use that to cancel a specific job, and other options that you can also list with this help command. See that it's still running. Yeah, it's kind of executing one CS6. So it's a wafer on one wafer scale engine. Switch back. So yeah, so we see the previous runs on the Sambanova are done. Let's see. Yeah. So this should be a typical output. So basically, kind of run this code, it bunch or dumps a lot of information on the compilation, and even the machine status before and after the job. So we should be able to see that. And yeah, so it's kind of ran on the SM30 RDUs. On the Graphcore system, so we see the example that we have launched. See this BERT example. So it's running with different number of steps and kind of prints those metrics as the work progresses. Yeah, towards the end, we see the metrics that we see with the global batch size and the number of steps it took, what's the throughput in samples per second. Yeah, so while the Cerebras job is running, so maybe let's switch to the next system, that's the Groq. So as I mentioned, again, Groq is primarily an inference engine that's used for running different applications or benchmarks. And the configuration that we have is, so from your local machine, you SSH to groq.ai, .alcf.anl.gov, and or you can also you land into one of these login nodes, login 01 or login 02. And then from that login nodes, the two is either you can SSH to one of these compute nodes. So there is the notation is RO1-GN01 all the way through GN09, and you can SSH to any of those nodes. this is one way, or the other way is you can also request a node using maybe an interactive allocation using QSub. So again, for running these hands-on examples, so there is a prerequisite when we create these virtual environments. So we've listed all the instructions here, and basically setting up the virtual environments. And Groq has this Groq as a software and examples that's called as Groq Flow. Again, we have provided instructions on how do you clone them, how do you install those examples. For Groq, the scheduler we use is a PVS scheduler. It's kind of equivalent to Slurm, if you're aware of that. And we use this commands like qsub and qstat to submit the jobs or get the queue information, and it is equal commands to delete a job. So for example, as I mentioned, if you want to have access to a single Groq node on an interactive basis for 1 hour, so we kind of use this command. Again, you can use the other flags, for example, that are listed like number of Groq accelerators. So for this, we have also provided a few examples. So for the hands-on, we can use as a BERT example. Now, if you look at the Groq flow, there is something called as proof points. So for example, there are the codes that are that you can just launch them on this Groq chips or the Groq node, and then you can try tweaking those parameters and try to see their behavior. So for example, let's switch to the Groq rack. Yeah, so I'm on a Groq login node. So I'm on the Groq login O2. Maybe I can just pull up a Groq node on an interactive mode. So I get a node on interactive basis where I can run this example. Okay, so if you look, so I've got access to this Groq R01-GN08. So again, for the Groq flow, the proof point of the examples, I've already listed or I've copied them here into my folder. So we call it Groq flow, then there are proof points. And if you look at this, for example, so there are like different applications with a computer vision, the speech NLP. So let's switch to the NLP for our BERT example for today. We set up this Groq flow software environment. Yeah, so now once I created this Groq flow, it's already there. So let me try running this BERT Trainees. So once the scheduler owns, we have already on the chip, so it will kind of start running our model. And we have also provided a sample output here. So yeah, if you see, yeah, it's kind of running because already compiled. So, but again, so once we run this command, so it kind of exports the PyTorch on Onyx file format and then compiles and run this model. So towards the end of the run, so we see the kind of some metrics. For example, they've provided using the Groq versus CPU. You see the accuracy, the end-to-end latency, and the latency, and also the IPS metrics. So here we are running this example on the inference mode on this each Groq chip, and you should be able to see the output as listed here. So for homework problems, we've also listed. Now, what happens if you want to change if the custom input instead of a dummy input? We just try that out. So you should be able to look at this code and see where you can tweak that and maybe just run that sample script as well. So there are additional examples that we provided. There's a ResNet 50 and there is a Mini LM V2, which is again a large language models, but it's kind of truncated version. So it's a mini LM, and the way we run is again it's still the same. So we over to the specific example, we activate our Groq flow environment, and then you run that particular job. And you should be able to see kind of a similar way for this particular example. And towards the end, we should be able to see what's the accuracy metric. So here it's a particular the rank correlation coefficient and the latency and IPS metrics as well. So if you want to, so this was done using an interactive allocation. You can also just submit your jobs using QSub, and that should take care of getting those resources and just running on that particular example. Towards the end of this page, we also included some documentation to the ALCF page. There is a repository of a few Groq examples that you can just try it out. And as I mentioned, so we're kind of looking at very simple examples, trying to getting hands on the system and how do we run these codes. And there are, if you go to this our internal ALCF page, so it has more detailed documentation on, now say if you want to take your own model and maybe run on one of these systems. For example, if there's a software on Sambanova is called Samba Flow, there's some documentation on our page and even on the Sambanova page where you understand how do you take your model, how do you refactor it to suit that particular APIs, and then once that is done, you can use the scripts that we listed to run these jobs. Again, these are all kind of simple examples, and if you want to try more detailed ones, we have listed on this ALCF page. You can please feel free to run a couple of those as you think. Yeah, so I think that's all I had for the content today. So we see the Cerebras system. Yeah, so even the Cerebras example, so we see here, it began this run. So we're running for a couple of steps here. You look at those metrics which are logged. And yeah, so if you look in the CSATL, the job executing is done. So this kind of gives a simple way to use this sample scripts and just run some of the sample examples that we have provided. And if any further questions, feel free to reach out to any one of us. We are happy to help. Yeah, I think that's all I have for the session today.
Thanks so much. So we have some time until we've about 20 minutes until we transition over to our science speaker. So I think maybe giving folks the opportunity to work on this on their own for maybe 10 minutes and then coming back if there are any questions. I think I'm also going to maybe pause right now and see if there are any current questions that folks might have before we dive into hands-on for about 10 minutes.
Again, feel free to get started on one of these machines because you have to set up this virtual environment, the software environment, and then you run this example. And again, you can post your questions on the Slack channel. So we have team members who are also we can help you with any questions that you have.
Excellent. Okay, so I see 54 on my clock right now. We'll give about 10 minutes, come back, and then have any final thoughts or questions then. So. Seeing silence and no typing in Slack, I think we can sort of wrap for today. So thank you so much, Murali.
Thank you.
Yeah. So we're going to transition over to our science speaker. Now, as I pull things up. So today we're shifting into the realm of cosmology. And we're going to be hearing from Nesar Ramachandra. Nesar is a cosmologist at Argonne National Lab with interests in the dynamics of large-scale structure formation. He's also working on the implementation of state-of-the-art statistical and machine learning methods for cosmological data analysis and fast prediction tools. So with that, I will transition. I'll hand things over to Nesar and let him get going.
Thanks for the introduction, Paige. Can you confirm you can see my screen right now with the slides?
Looks good.
Okay, thanks. Okay, so this is a talk on AI for cosmology. Like Paige mentioned, I'm a computational scientist at the Computational Sciences Division. I've been working, my background was in physics for my PhD, and since then I've been working on a lot of AI methods, working with a variety of data sets. So in this talk, I'll highlight a subset of AI for cosmology efforts that are being done at Argonne. Some of the common themes in this talk will be how do we use simulation data or synthetic data, and how can they enhance our understanding that comes from astronomical observations. We'll also talk a little bit about Bayesian schemes, probabilistic schemes rather than point predictions. Some of the emphasis will be on explainability or interpretability of AI algorithms and why they are very important for science use cases. And finally, I'll go over a small case study where we'll see some of the image processing pipelines for denoising, source separation, some probabilistic classification, and understanding representation space. Okay. Just a quick introduction to cosmology in like 2 slides. So the universe started with the Big Bang about 13.7 billion years ago. And since then, it's been expanding. And recently, this expansion has also been accelerating. Initially, so we have a few million, in few 100 million years, we had first set of galaxies. Then we have a lot of planets forming at around 9 billion years. And here we are today. And how do we know this? We know this because we have observations from a variety of telescopes at different points of time. So when we point a telescope at the sky, we are essentially looking backward into the history of the universe, and we have observations that start all the way from around like a few seconds or a few minutes after the Big Bang, all the way until very recent cosmology. But if you look at the state of the universe right now, what we see in the universe is called baryons. That forms very small percentage of the universe, about 4.6%. A lot of it is something called dark matter and dark energy. And dark matter is about 23%, and dark energy is about 72%. So a lot of the universe is sort of unknown because all we see are these atoms, and from these we try to infer what is the rest of the universe made of. Below here, we have a small simulation of a very large simulation and a very small snapshot of it. What you saw in the beginning, what you saw in the beginning is what's called the cosmic web structure. This is how the dark matter is distributed in the universe. There are places where the dark matter is not very dense, and there are places where it's extremely dense. Those are the bright spots that you see here. And the places where it's very bright, those are places where we have galaxies. And all the solar system, all the stars and everything are essentially located in these extremely dense bright spots that you see. Again, coming back to our current universe, we have a lot of constants that prescribe what our current universe is. So there are constants like Hubble constant, cosmological constant, dark energy density, dark matter density, etc. And these essentially are just a bunch of scalar numbers that prescribe the state of the universe. What's really interesting is how precise these values are inferred from the observations. So as you can see, some of these things like baryon densities, it's up to like 0.001. And this has been possible because of a lot of statistical analysis that has been carried out from observation data. And this is also one of the important aspects when we deal with like AI systems. Can we get our AI inference to be as precise? Can we make them compete with our current Bayesian analysis techniques? So this is an extremely important question. And I would say this is sort of the bottleneck that is required before AI becomes AI transits to a real use case example in cosmological studies. Sorry, yeah. Next, how do we do these studies? So there are essentially two parallel efforts. So there's an observational effort, so that we have a lot of ground-based telescopes and space telescopes. You may have heard of James Webb in the news recently. There is an upcoming telescope called the Vera Rubin, where our team at Argonne is heavily involved in. So these telescopes look at the universe in different regions of the light. So there are observations that are made in gamma rays. There are observations that are made in optical, infrared bands, and radio bands, etc. So these are all from different telescopes. And they sort of map out the universe and observe the galaxies. And on the other end, we have these simulations that are run on extremely large supercomputers. At Argonne, we have this hack team, which creates these massive large-scale structures of the universe. And these simulations are extremely expensive. And essentially what you're trying to do is you're trying to bridge this gap between observations and simulations in the end. And the plot that you see in the center here is, let me see if I can get the pointer. All right. The plot that you see in the center is actually distribution of galaxies that is coming from observations in two of the pies. And the red ones are coming from the simulations directly. And you can see that geometrically, at least, there is a very good match between how the galaxies are distributed. However, with all the cosmology studies, like in any scientific studies, there are a lot of caveats that come along with the domain. Some of the caveats that I managed to list are things like multimodality. So cosmology datasets, be it observational or simulation-based, can come in multiple modes. So we have graph datasets, we have images, plenty of images coming from telescopes. We have a lot of time series, summary vectors, scalars, and more recently, there's a lot of emphasis on text knowledge. That's in the papers and the textbooks and everything. So a lot of different types of datasets. And as opposed to datasets that we often get by scraping the internet, the cosmology datasets tend to be extremely expensive. So this is because the simulations are run on supercomputers covering thousands of nodes. Observations are often billion-dollar investments that are run and observed over a wide time scale. So this makes using the data or access to data not very easy sometimes. And the other important thing is multifidelity. So the data often comes from different sources. So if it's simulation, we may have data coming from multiple resolutions, different approximations, or different physics models. And when it's observations, you have a lot of data that has different types of noise behavior, lots of systematic effects that are not easily quantified. So essentially, transfer of knowledge is not very straightforward. So the cartoon that I like showing is we cannot expect to have like a deep neural network or something that is trained from cartoons of cats and try to infer whether a real image of a cat can be inferred when in deployment. So this is very important when it comes to cosmology studies as well. If we have synthetic data sets that's based on crude toy models, that may not translate well to observational studies. And apart from the quality of the data, there's also no assumption of fair sampling. What I mean by this is, when we do our observations, there are a lot of things that are not covered. So there are types of galaxies that may not be observed easily. There might be galaxies at very high redshift, which is like very vast distances that might be so dim that our data sets just do not have them. And nearby galaxies, bright objects might be biasing your data sets more. So understanding the data, understanding the priors that come into your analysis just based on the data distribution is very important. And so this is on the data side. And whereas when it comes to analysis, like you saw earlier, the error requirements or the error budget in cosmology error budget is very low. So with precision cosmology, we are reaching like 3 sigma to 5 sigma errors, which is being possible mostly because of these very sophisticated Bayesian statistical analysis. And it's often not very easy to get similar levels of precision with AI methods. Other thing that is important is, even though a lot of times we go with purely data-driven technologies, there are a lot of prior domain knowledge. There are simulations that are run with certain known physics. There are conservation laws, and all these things actually help us a lot in constraining our physics parameters. So considering all this, I'm going to show a few examples of how we used different types of AI systems. The first one is this conservative idea where we keep most of the Bayesian pipeline the same, but we replace a small part of the entire Bayesian pipeline by an AI system. So what's happening here is a typical Bayesian inference using MCMC sampling, which tends to be a very expensive thing to do. That's because often the forward model that we use in Bayesian inference can be very slow. And what we did was we essentially replaced the forward model with an emulator that uses a Gaussian process and a variational autoencoder, and that sort of emulates these vectors that you see for different cosmological parameters. And then it can be plugged into a traditional Bayesian inverse program. And what you see on the right is the constraints that we got from using this AI system. So essentially, we are able to get extremely good constraints. So what you see there are the posteriors and like the 1 sigma and 2 sigma levels. Extremely good posteriors just by using this AI-based forward model. And what's really cool is something like this may take like weeks to months to run with actual simulations, whereas if you use these emulators, this can be done in like half an hour. The next example I'm going to show is a little less traditional. So this is something where we used a GAN-based model. So essentially what's happening is there is a wide variety of Subaru telescope. It's a telescope based on a Japanese survey. And it kind of like scans the sky, observes a lot of different objects. And galaxies come in various flavors. So galaxies, the most commonly known galaxies are these elliptical galaxies and the spiral galaxies. But if you actually look at billions of objects, you'll find very few objects that are anomalies. And there are like extremely low number, and it's often not very easy for somebody to sift through all the billions of images and find these important ones or interesting ones. So we managed to have this, the GAN-based anomaly finder. Essentially, it looks at the latent space coming from the GAN and finds out what are the anomalies in the latent space. Just from the observation data, we managed to find a whole bunch of anomalies. And the idea is that once we find this, we give it to domain scientists, and they can look at these individually and study them separately. And as it turns out, one of these images was actually extremely important, and it was sort of like a new type of galaxy that was never observed before. So a lot of follow-ups are possible just based on, just possible because of enormous computational capabilities that we have. Okay, then coming to a slightly more involved case study. So I'm going to show something called strong lensing example. These are also very rare objects in the universe. Essentially what happens is, if there's a galaxy that you're looking at, and let's say there is a galaxy behind it, the light coming from the the distant galaxy gets warped because of gravity, according to Einstein's general relativity. And what you observe is sort of this arc-like images. So often you see these foreground galaxy, which is bright, and then in the background you see these tiny arcs that are not real, but it's only happening because of some sort of lensing effect. So this is called gravitational lensing, and although it's very rare, it's extremely important, because from this we can understand a lot of information about how the dark matter is distributed in the universe. We can also understand a lot of quantities related to expansion of the universe. So this is an extremely important study. But the problem is that currently we have very few data sets. Currently we have very few observations that are actually made, in the order of hundreds, and not at all enough to train any AI model. On the other hand, with telescopes like Vera Rubin that's coming up in the next few years, we're expecting to find millions of these. The problem is, with Vera Rubin, there's going to be something like 37 billion objects. And in that, a few million are going to be these strong lenses. So finding those and getting quantities out of them is an extremely difficult task. However, simulations come to rescue here again. The great thing is the physics models that describe how these lenses are formed are quite straightforward, and we can perform simulations and get millions of these images. And that's exactly what we did. We have these cosmology simulations where we try to find these, extract the data sets that are related to these lenses. So we have like few million of these simulated images. And the good thing is these simulated images are extremely close to what reality is like. So once we have that, we had this AI pipeline. So the idea was instead of performing the entire task in one go, we wanted to have multiple modalities. So each modules that are in this AI pipeline would perform one specific task that corresponds to a task that is done in traditional astronomy. So the first step was a denoising. So we used like a enhanced super resolution network for this, where an image that comes in, a noisy image will just be denoised. And the second task is a deblending task. It's called also called a source separation. What we do here is we remove the foreground from the background, and what's left is just the background. So that's what you see in the third image there. And finally, based on the image, the background image, we have a classification network, just a binary classification that tells us whether the image is an actual strong lens or not. And if it's a strong lens, then we can infer some of the physics parameters. So the cool thing about this is when we have these AI modules, each of these modules can be independently trained and tested just because we are using the simulation data. Because in simulations, we have access to every region of our simulation. We can essentially probe that and use that in training the networks. And the other thing is, because we have this enormous data, we can also cover those gaps that I talked about, like, in the observations, the places where you do not see, those can be filled up with simulations. And that really helps in increasing our classification benchmarks. Okay, and a few more examples of what this analysis looks like. The top row here is the incoming images, which is noisy. There is the foreground and the background. And the second row shows the target that is coming from our simulations, which is basically a denoised output. And the third row shows the performance of our first module. So all it does is the denoising part, and you can compare between the second row and third row to see how well it's performing. And the last two rows are the source separation. So you're essentially removing that bright spot in the front, and you're left with only the background. And again, you can see the performance between the two. And what's really nice with this analysis that we did, and I think it's very important in most of the scientific studies, is also this concept of interpretability and uncertainty quantification. Interpretability wise, the good thing is, so we use this variational information bottleneck system. What it essentially does is, if you look at our latent space for classification or regression, you see that a lot of these strong lenses are divided nicely in the latent space. So I'm showing all the lens systems in the latent space right now. And if you start zooming into regions of it, you find different types of lenses, which is really nice to see. There are lenses that are sort of incomplete. There are lenses that look like complete circles. So based on geometry, they're just sort of divided in the latent space, which is nice. And the other thing is how well are uncertainties. The uncertainty quantification, more often than not, the emphasis should be on how what that uncertainty means. So here, the great thing was, if you look at the latent space and plot it against the error bars, we had these like two modes for lens systems and unlens systems. And the color is based on the error magnitude. And you can see that, where the two modes touch are where you have more of the misclassifications. And that's where you have your error bars being high as well. So the confidence level is actually low in regions where there is more misclassification. So this is a sort of interpretability that's really nice and desirable in a lot of AI applications in science. Finally, I'm going to conclude I'll keep this slide. So basically, I wanted to say that cosmology deals with a variety of data modalities. There are a lot of sources that come into picture, from observations to simulations. Simulations are often extremely necessary, but we have to be very careful while using simulations. So we have to make sure the experimental design is robust. We have to, we need an extensive validation and benchmarking. At the same time, because we are dealing with synthetic data, it also makes uncertainties and interpretability very important. So with that, I'll take questions if there are any.
Great, thank you so much. I saw that there were a couple questions that popped through the chat that as you were speaking, and Carlo very kindly got to some of them, but I don't know if you want to speak to any of those questions.
Oh, sure, yeah. So dark matter. So Will is asking if dark matter and dark energy are both beyond standard model. Is that right? Actually, no. So there have been several standard models of cosmology, but the current standard model does involve dark matter and dark energy. The type of dark energy model defines what beyond standard model are. So there are dark energy models that involve different types of dark energies, or varying dark energy that varies with time. So there are inflationary models that are different. So these are essentially what constitutes beyond standard model.
Great. And then there was one question about observations, of what observations were available a few seconds after the Big Bang.
Oh, the nicest one we have is called CMB, cosmic microwave background radiations. And if you look at the sky, you often see this like sort of heat signature that is coming from a few seconds after Big Bang, I think. And that has been instrumental in constraining a lot of our cosmologies.
Great, thank you. There was one comment in our Slack that I wonder if you would speak to. Alfred asked or spoke to, I thought there were a few recent discoveries that challenged the age of the universe in the current model. Can you speak to that?
Yeah, I think there have been a few of those. One thing that has happened, well, not exactly age of the universe, but that some of the things that have come up recently are from this James Webb Space Telescope. We've started, they're claiming to have found some galaxies that were formed much before what standard model predicts, some of the older galaxies, and that was sort of extrapolated to the age of universe being more than what we think. Yeah, so it undergoes enormous peer review. So we'll wait and see for these results.
Perfect. Okay. Well, thank you so much, Nassar. I think we have run out of time.
Sorry, just one clarification, and I have to thank Esteban for this. CMB was actually not from few seconds after Big Bang. It was 300,000 years after Big Bang.
Okay. Yeah. Perfect. Yeah. So, which is, you know, a couple orders of magnitude different. Awesome.
Yeah.
Okay. Thank you so much, Nassar, for coming and speaking today. And with that, I think we'll wrap session 7. Thank you all for sticking around, and we'll see you next week for our last session for the series. Bye all.